That's completely cool. You tried to get the last equation to only have z. So that's like the Gaussian elimination, where you're trying to basically get the last equation to have z, the second equation to have x and or y and z, and then the first equation can have x, y, and z, right? Do you feel like you want to use that method? Because it does say solve the system of linear equations and check any solution algebraically. So it doesn't specify that we have to use Gaussian elimination for that. I mean, we can do it that way, or we can try it the other way and, you know, do that. So I say, let's try to, you don't care which way we do it. You just want it to be done, right? All right, so let's see here. 7, 3, number 25, okay? And we have x plus 2y minus 7z equals -4. And you guys are going to have to, this one, yeah, to make sure that I don't forget any numbers or negatives. That would be bad. 2x plus y. There's something about when you do it on the screen, I don't know, plus z equals 13. Okay. And 3x plus 9y minus 36z equals -33. Okay, so what I'm proposing that we do for this problem is we could use Gaussian elimination and get it down, but I think the method that's slightly easier is if we use the method of substitution for this problem. And what I'm thinking is that we could first maybe solve this middle equation for z and then substitute it into our other two equations. So let's try that. So z would just be 13 minus 2x minus y. Okay, so then we're going to take that z and we're going to substitute it into our other two equations. I meant to ask you, Jennifer, you just need help solving the whole equation? There's not like a specific part. I'm going to keep writing while you type back. So we have x plus 2y minus 7, and then instead of z, we're going to put 13 minus 2x minus y, and that equals -4. So then we're just going to we're just going to simplify this, right? So x plus 2y, 13 times 7. What's 13 times 7? Any of my fast math people in here? 91. Minus 91 plus 14x. Okay. So I was wondering if that's where you're going to get plus 7y equals -4. All right. So you ended up with some solutions, but it has some a's in it, right? So I was saying you ended up with a solution, but it kind of looked weird. Is that what you're getting at? Oh, okay. Your solution didn't match up with the books. Because this problem actually has something kind of interesting about it that we didn't specifically talk about in class. So if you did this problem or didn't do this problem yet, it does have kind of an interesting solution. And that is that um, one of our variables, it doesn't matter what you put in for the variable. So kind of spoiler alert, that z actually, it doesn't matter. You can put any value into z. So it could be any number for that. So we didn't actually do a problem like this in class. So that's why I was kind of wondering if it was something with making the solution or not. So let's just keep going. I will try to go as quickly as possible. So we've got, all I'm doing right now is I'm substituting z into the first equation. So now we have 15x plus 9y. And I'm going to move my 91 over to the other side, and I get equals positive 91 minus 4 is 87. So this is my first equation that I've substituted z into. So now I have one of my two equations. Okay. And then my second equation is going to be this, the second equation that I'm going to work on is my third equation. Okay, so I'm going to take this down, and I have 3x plus 9y minus 36 times z. And z is going to be 13 minus 2x minus y equals negative 33. All right, so now I need to simplify by distributing my negative 36, right? 9y. 36 times 13 is 468. Minus 468 minus, nope, plus 72x plus 36y equals negative 33. So now I'm going to do some cleanup work. So I have 72x plus 3x, so I have 75x. And I have 9y plus 36y, so 45y. Okay, and then I'm going to move my negative 468 to the other side and subtract 33, so equals 435. Okay, so now I have two equations and two variables. So basically what I did is I took my middle equation, I solved for z, and then I took z out of the equation by substituting it into my top and my bottom equations. So now I have two equations with two variables. I have 15x plus 9y equals 87, and I have 75x plus 45y equals 480 or 435. So now I just need to extend my paper by a lot because now I have two equations with two variables, and I can solve for one of those, right? Hopefully. All right, so let me just rewrite these down here. These look like they might be, I have 15x plus 9y equals 87. And I have 75x plus 45y equals 435. All right, so now I want to eliminate one of those two. I'm going to be, I don't know what method I want to use. I feel like I could divide everything in the second row by a number to simplify it. I know I could divide it all by 5. I'm just debating, how do I want to simplify? Oh yeah, divide by negative 5. And you know what actually happens is that I end up with the same solution. So I end up with the top one stays 15x plus 9y equals 87, right? And then the bottom becomes, if I divide everything by -5, right, Aiden? Then it becomes negative 15x minus 9y minus 87. Right, so then I've basically eliminated my solution. I've basically said, okay, well, yeah, divide 0 by 0 and everyone is happy. We love that in math, right? We love it when that happens, not. So what that means is that our z value that we found has infinitely many solutions. Okay, because I picked z, and that was kind of just out of I don't know what you want to call it, just because it looked the easiest. Because we get the 0 equals 0, that means that it's true for many values. Okay. So this is the part that we didn't talk about. Because we figured out that it has infinitely many solutions, then we can just say, well, we don't want to completely give up on our original set of equations. Okay, but we're going to say instead of z being some value, we're going to actually solve our top two equations in terms of some just constant. So, all right, I don't feel like I'm explaining it very, very well, but let me now make my paper go further this way. Okay, so we're just, because z doesn't matter what we put in. If we put in any z, we're going to get the same two equations at the bottom, is basically what I'm saying. Because we solved for z and plugged it in and we ended up with the two same equations. Z could be 0, z could be a million. It doesn't really matter. So what the book does and what mathematicians do is they say, oh, well, z could be any real number. So we're just going to call that k. So I don't know if you looked in your book and saw a k, or if you saw an a maybe in your book. But basically they're saying it k, which k represents any real number. Okay. So then if I wanted to solve for x and y, then you're just going to plug k in for one of your z's. So to solve for x, this is my easiest equation. Okay, so x does have some value, but it all depends on what real number you put in. So x will be x plus 2y minus 7 times some real number that you pick equals -4. Okay, and then if we solve for x, we're going to get x equals -2y minus 7k minus 4. Okay. And then let's keep going. Yes, thank you. So you guys got to keep me on my toes, plus 7k. All right, so then let's take our second equation and let's plug that in with a k. Okay. And again, this is kind of a special case one, so I would expect this one to be a little bit complicated. So now we have 2 times x, which x was -2y plus 7k minus 4. And I'm running out of room again. okay, plus y plus z, which is just k, equals 13. So we're getting there. Let's distribute our 2, so we end up with negative 4y plus 14k minus 8 plus y plus k equals 13. So we're finally going to get to what y is. So we've got negative 5y, right? I'm just trying to combine too much in my head, plus 15k equals, and then 8 plus 13 is 21. If I did my math right. Negative 5y equals 21 minus 15k, or y equals negative 21 fifths plus 3k. So this that I just ended up with is different from the solution at the back of the book. I was going to say, how would it be 3? Oh, yes, it would be. Because I'm like, this is not, thank you. That would make a big difference. Because we had negative 4y plus a positive y. I'm like, this is not going the right way. That will help my solution greatly. All right, that's much better. So we get everything divided by negative 3, so we get negative 7 plus 5k. That's much better. Okay. Then to solve for x, you're just going to put that back into this equation up here, this orange equation. All right, so that was a super tricky one. Obviously, most of them will not be like this. You'll just be solving. But that should look closer to what the solution is, how they ended up, or if you get an A or something like that. Okay. Does that make sense, Jennifer? Okay, awesome. What I was going to try to do with this problem, and I honestly don't know how your matrix calculator will deal with this, but since we're in this section anyway, I'm going to, if you have your homework done or not, if you have it in front of you, if you pull out number 23, and we'll try it with number 25 too, but I kind of wanted to give you a, we won't say. I kind of want to give you a taste of all of this work that we've been doing with matrices and why it actually is really powerful. And I think your book kind of skips over it really fast. There's like one little blurb about that you can use this for matrices, but they don't really go into a whole lot of detail of it. So let me just give you a quick review. We pretty much finished 7-6 on Monday. I think we might have a problem or two more to do. So we've been talking about matrices, and we've been talking about in 7-6, we specifically talked about how to find the inverse of a matrix, right? So if you take a matrix and you multiply by its inverse, then you end up with the identity matrix, which looks a lot like what you would expect the number 1 to look like in matrix form, okay? And so we did some problems with how to find the inverse of a matrix, and we'll do a few more of those. I showed you the book method of how to find the inverse of a matrix, right? So the book method is by making a double matrix and then kind of doing some transformations on that. And then there's also a method where we use a determinant. And so we'll talk about that just to review it. But I kind of want to give you hey, this is why I think one of the most powerful things that a matrix can do, and the book kind of skips over it. I mean, at the end, we do talk about some applications of the matrix, but they don't really, I don't know, they don't really emphasize this. So since we're in this section and we're talking about inverse of matrix, I just want to point out, if you have your 7-6 notes, there's this one little blurb right before it says a system of equations with a unique solution. So if A is a matrix, the system of linear equations represented by ax equals b has a unique solution given by x equals inverse of a times b. So that it's easy to skip over and look, but what I really want to do is show you how powerful a matrix can be, especially since we just spent, I'm sure when you're doing your 7-3 homework, you're like, there's got to be an easier way to solve these, right? Well, there is. So I'm back in section 7.3. And if you've done your homework or haven't done the homework, it's okay. This is, well, hopefully you've done it. So this is 3x plus 3y plus 5z. So this is just the problem that you probably solved or will solve using a long complex. Either you're going to, simplify it down, or you're going to solve for one variable, and it's probably going to take up a lot of room on your paper, right? But I just want to show you how powerful matrices can be in solving these kinds of equations. Because my Algebra 2 text really does a great job, I think, of kind of showing the power of matrices, but this book is kind of like, yeah, you can do that. It has one little blurb. All right, so let me decode a little bit. So this is problem 23 and 7.3, but in 7.7 or 7.6, yeah, 7.6, we're talking about the inverse of a matrix. The inverse of a matrix. And so this inverse matrix actually can be really, really powerful when we want to solve systems of equations. All right, so what I mean by that is I think it's easier to show you, and then I'll kind of step back. So if we took this system of equations from 7.3 and we changed this into a matrix equation, okay? So what that means is that I'm going to have a 3x3 matrix that contains my coefficients. So I have 3, 3, 5, 3, 5, 9. Are these really all plus? Yeah, they are. That's nice. 5, 9, 17. Okay, so all I did is I took the coefficients of each of my variables and I put it in a 3x3 matrix. Then I'm going to multiply that by my variable matrix. So x, y, and z. So now that you guys understand how you multiply matrices, you can see that if I multiply my matrix out, I would have I would basically have 3 times z plus 3 times y plus 5 times x, which will give me my first equation. So now that you understand matrix multiplication, it's going to be your first row times your first column, right, to get your first entry over here. So you can see that that multiplication works out. Does that make sense? I'm going to erase this part. So basically, if I was multiplying this 3x3 times a 3x1, I would end up with a 3x1 that would be 3x plus 3y plus 5z, right? And then so on. So all of my equations would pop back up if I did that matrix multiplication. So if I do that, and this is where I'm going to erase this because it's going to get really messy if I don't. There we go. I know that multiplication works out, but I also know on my other side of my equation, I know what the values are. I know that my solutions are 1, 0, 0. Okay? So some smart mathematicians a long time ago figured out, well, this looks an awful lot like an equation, right? If I just call these by their matrix name, so let's call this guy A, right? Matrix A times some variable matrix, and we'll just call that big X. Okay, it's hard to make a big X in here, but that's my big X matrix. And I can even put little brackets around my matrices to make it really clear. And then that equals some matrix B. Okay, this looks a whole lot like an equation where we could solve for X, right? Now, in our algebra history, before we might just divide by A, if we could do that. But we can't do division with matrices, right? So our other option, instead of dividing by A, is that we could actually multiply A by its inverse, which is what we spent a lot of time in 7.6 figuring out what to do, right? We figured out how to find the inverse of a matrix, so let's actually use it for something. This is the little nuance with it, though. We want to actually, because you can find your inverse in any order, it matters which order you multiply in. So what I mean by that is we could say, oh, if I take the inverse of matrix A times matrix A times X, then I also need to multiply the inverse of matrix A on the other side and multiply that by B. I promise I'm getting there, and it's exciting-ish. Okay, so the inverse of matrix A times the inverse is just the identity matrix, right? Just that ones and zeros. So this actually just leaves me with X equals the inverse of matrix A times B. And this equation is true for any, we picked a three equation, 3 variable problem. But if you had 4 equations and 4 variables, you could use this to solve your values if you have any higher number. So let's see practically what this looks like. Promise we're almost there, okay? So if I get a matrix calculator, somewhere I have one up here. This is the Desmos one because I think it's kind of cool. They have a new one. I like to try it out. Okay. Let me make a new matrix. It's going to be a 3 by 3. Okay. And this is called matrix A. So I'm going to fill it in with my coefficients. So my coefficients were 3, 3, 5. The second equation, the coefficients are 3, 5, 9. And my third equation, the coefficients were 5, 9, 17. Okay. And then I think to enter that, I just hit enter. Yes. Okay. So I have my matrix that represents my variables over here. Okay. And then I need a matrix that represents my answers. This is my B, right? That's my answers to my matrix equation. So new matrix, and this is going to be 3 rows and 1 column. Okay. And the solutions are 1, 0, 0. So now that I've entered my problem in, I can say that I want to do the inverse. No, I guess I have to write that. I have to do A inverse times B. And now I actually have the solution of my equation. So X equals 1, Y equals negative 1.5, and Z equals 0.5. Kind of anticlimactic, but the fact that I can just convert my my set of equations into 2 matrices, and then the only calculation I have to do is the inverse of A times B, and then it calculates for me, it's pretty awesome, I think. And the book kind of skips over it, like, yeah, you can do that. It has a little blurb in there. But I think it's a really powerful calculation, especially if you are dealing with like a really big matrix, like a 5 equation, 5 variables, and you want to solve all of those. Can you imagine how much paper that would take? So did that make sense at all? I don't know why, Aiden, but yes, Jennifer and Aiden, I'm glad it makes sense. I don't know why. I teach this in Algebra 2 also. It's a little longer matrix chapter, and like you do all this hard, it's the same thing. You do all the hard work, and then at the end they're like, and you can just do this to find the solution. Um, but this book is just kind of like, oh yeah, you can kind of use it to solve, you know, unique solutions. So where I think this breaks down is I was in number 25. I think that this is going to break down. I don't know what Desmos is going to do. I'm willing to try it, but if you do look at your book, it says if a system of equations with a unique solution. So I don't know if this is going to work for 25. It might break Desmos. I don't really know. So let's try it. Number 25, this is number 25 and 7.3, the one that we just spent time doing, right? So I'm going to put in the coefficients for that. And we're going to see what happens because I honestly don't know how that will appear. 1. So what I'm doing right now is this is number 25 and 7.3, and I'm putting in the coefficients of my equation. 3, 9, negative 36. And then up 1, 1, 2, negative 7, 2, 1, 1, 3, 9, negative 36. I'm wondering if this does not have an inverse, and that's why we're getting this error. So it doesn't really matter if I put in the solutions. There we go. So it's telling me that singular matrices do not have an inverse. That's even more information than I was expecting. Basically, matrix A does not have an inverse, so I'm not able to use this kind of simple formula to find the variable, you take the inverse times the solution, because if we don't have an inverse, then you can't use it. And I'm guessing oops, that's not where I wanted. I am not 100% sure, but I think what is happening in here is that one of these, and yeah. I honestly don't know off the top of my head why we don't have an inverse for that. I'm thinking that I'm not sure. I'm not sure if the determinant of this is 0. It could be that the determinant is 0. Let's try that. So remember, we talked a little bit about the determinant. So let's try the determinant of A. That's why. Yeah. So remember, it's not what I meant to do. When we talked about finding the inverse of a matrix, right? I showed you the book method, and then I showed you how you can do another method where you multiply by this thing called the determinant, and then you kind of multiply it by the matrix. And so in this case, the determinant of this matrix is 0, so you're multiplying the whole matrix by 0, so there's no inverse. Okay, so that was a bunch of words, but that's why number 25 kind of has a weird solution, right? And the calculator doesn't work. But if you pick another one, I don't know off the top of my head, if you pick any of the problems that you have been solving by hand in 7.1 through 7.3, you should be able to use this method. So you could use it by, when you have a 2 equation, 2 variable, 3 equation, 3 variable, all that. So I really wanted to show you that because I think it's powerful. I think it's a really A really powerful application of matrix. All right, any questions about that? Nope. All right. Cool. So what again makes those equations broken in the first place? Oh, like this one that's broken? Oh, so Aiden, this one, um, I believe that this one, well, number 25 has more than one solution because the z variable, at some point, one of these equations is the same as the other equation, right? We got down to when we substituted for z, the two equations were equal to each other. So that means that the value of z doesn't matter. So z basically has infinitely many solutions. And so then once you know that z, and then we knew that z had infinitely many solutions because when we plugged z into the other two equations, they ended up being the same equation. So it doesn't matter what we put in for z. So z, just the variable z can be any real number. I mean, it's kind of I shouldn't really say infinitely many solutions, but you kind of think of it in terms of z could be anything. And so then once we know z could be anything, then basically we just need to figure out, well, if z is any number, what can my x and y be? And then it kind of breaks down here when you're using a matrix calculator because of the determinant of that. Sure. Okay, so we have a slight bit of time left. I'm going to show you, I think we talked a little bit about this, but I want to show you how to find the determinant by hand. Um, a, a 2 by 2 matrix is actually really easy to find the determinant of. A 3 by 3 is a little bit more tricky, but not impossible. So I want to show you those, and then honestly, probably what we'll do is we'll do this today, and then we'll probably do it again when we meet back in, a week and a half, because your brains might be a little tired, right, after a break. So let me pull this up here. So we're going to talk about this determinant of the matrix and why it is important. And again, I don't think the book does a super great job of explaining why it's important. So we've done a lot of things, and they kind of do it in a backwards order. So we've talked about matrix, right? Matrix or matrices. And we know that we can add them together, right? If they have the same order, we can subtract them. We figured out how to multiply by a scalar, right? That's just multiplying, basically like distributing. And we figured out how to multiply matrices, right? And so we know how to do all these things, hopefully. And there's in 7.6, we talked about finding the inverse of a matrix. Okay, so the inverse of a matrix basically means if you have a matrix and you multiply it by its inverse, you get the identity matrix, which in a 2 by 2 is just 0, 1, 1, 0, 0, 1. Okay. In 7.7, you learn how to find the determinant of a matrix, the determinant, and you can see that up at the top. So I want to give you the why. Why do you find the determinant of a matrix? How does that help me? And then show you how to do it. So if you remember back in 7.6, when we were trying to find the inverse, the book had a specific method where you would write out your A, B, C, D. You would write out your matrix, right? And then you would write the identity matrix and kind of do this process to eventually get the identity over here. And then we would have our inverse over here, which works. Okay, that works as a method. So I'm talking about, I know it says under determinant, but I'm talking about back to inverse here. So this is when you're finding the inverse. Okay, another very widely, commonly common way to find the inverse of a matrix, and it's more of a memorizing formula, so maybe that's why your book doesn't emphasize it, is this. So if I want to find the inverse of matrix A, B, C, D, okay, I want to find the inverse, that's equal to the determinant times, and I'm running out of room, the determinant times, and then it's D negative B negative C A. So you switch these two variables and then you make these two negative. So this, and I think I showed you guys this in a real problem, right? I showed you, oh, if I want to find the inverse of this matrix, I find this thing called the determinant, and then I just multiply that number. The determinant is a number. It's not a matrix. And then I multiply that scalar number by my original matrix, which has been transformed a little bit. And I think most people said that this looked a little easier, a little less messy than this, but either method works. I'm okay with that. So all that is just to say that the determinant does have a purpose other than just, we want you to find the determinant, because if you want to find the inverse of a matrix, it has a relationship in how you find the inverse of a relationship. And so that's why, I mean, I didn't mean for that to happen, but when we plugged in number 25, the problem number 25 that we were working on, the determinant was 0. All right. So if the determinant was 0, then when I multiplied my inverse, or when I tried to multiply to get my inverse matrix was going to be all zeros, which is not possible, right? So that's why the determinant is important, instead of just saying, here's how you find the determinant. Now, when you want to find the determinant of a 2x2 matrix, it's actually pretty easy. Okay, so to find the determinant of a matrix, help if I was on brush. So to find what the determinant is, if your matrix, I'm going to use A, B, C, D. Okay. What you do is you multiply, it's kind of like cross multiplying. It's A times D minus B times C. And I have, you know, I just realized I have an error. This should actually be 1 over the determinant. And so then that's really bad because our determinant was 0, so then we just really have undefined. So I apologize for that. I forgot my, yes. Anyway, so when you find this determinant, you're going to do A times B minus B times C to find the determinant, what that number is. So to find that number is actually pretty easy in a 2x2. When you get to a 3x3, it gets a little bit more, not hard, but just a little more, of course. Okay, so a few terminology things. You can see up here, I've been using the determinant DET, which is a common, you can say the determinant of A by saying DET of A. Another way is to write it looks like absolute value, right? So if it looks like they're asking you to take the absolute value of a matrix, what they're actually asking you to do is to find the determinant. All right, so then if we have, I don't have them up here. If we have some problems where we have to find the determinant, can make my writing a little bigger, right? Number 2 would be really easy. the determinant of number 2 would be just negative 10. Okay, the determinant of 4 is going to be negative 9 times 2, okay, minus 0 times 6. So the determinant of number 4 is negative 18. Right? What about number 6? Number 6 would be 3 times negative 8 minus negative 3 times 4. So we get negative 24 plus 12 or negative 12. What about the determinant of number 8? It would be 4 times 0 minus negative 3 times 0. So the determinant of number 8 would be 0. So I can tell you already that number 8, since it has a determinant of 0, it will have no inverse. Okay. And then I think we're just going to stop there. Number 10 and 12, there are several methods for finding the determinant of a 3 by 3 matrix. They take a little bit more explaining, so we'll just save that for 2 weeks from now. 2 weeks from now? A week and a half from now? Something like that. Okay, so that was a lot of different pieces of information. I know we didn't cover a whole lot of new sections, but I think that understanding why we're doing all these things is kind of, well, it is really important. Instead of just, hey, this is how you find the inverse. This is how you find the determinant. Now we know why it actually is useful. Oh, and yes, and just really quickly, your matrix calculator, obviously, if I put I don't even think you need to use a matrix calculator for this, but there is a button on there that says determinant of A, same thing in your calculator. So, all right, guys, thanks for coming today. Have a wonderful, wonderful spring break. I am not going anywhere, so if you have questions, send me an email and we can hop online sometime. But if not, I hope you have a good break and get to catch up or relax or whatever you're going to do. Oh, yes, and very happy Easter. Thanks. I forgot it was Easter. Yes, have a happy Easter. Bye, guys.